the in dimensions and optimal compressed sensing from mixing stochastic processes.
Okay, thank you very much. So I will talk about the recent work joined with Jonathan, and the title of the paper is the second part of the title of the talk: optimal compressed sensing for mixing stochastic processes. And mean dimensions in the title are able to attract some attention. But it actually makes sense. Mean dimension type ideas or objects do appear in our work. So let me start by giving a little bit of a historical account and try to unwrap those complicated words that appear here, starting with compressed sensing, which I guess might be the least familiar for you. So compressed sensing I guess yes, but I'm not sure if here. So compressed sensing. This is mathematically, this is simply a theory of compression of finite dimensional vectors by random matrices. Okay, but there are of course some twists. So we want to consider vectors. I will know them by x in Rn, and we want to consider, for now fixed but soon random matrices. N times n. Okay, and I assume that m is smaller than n, much smaller. Okay, and the task, which, well, the way I will put it at first, it will seem absurd. No. Here, for now, all those dimensions are fixed. Okay, so yes, exactly. But I will be a little bit more precise.
Fixes the dimension. The random is there, right? Often there is some understanding that we start growing.
Right. So actually, we soon will be working with growing dimension of matrices and the vector sequences. But for now, I am talking about the classical theory, and the dimensions are fixed. Okay. And what we want to do? So the task, well, the task is to recover the vector x from vector y, which is not a times x. Okay, so this is something that lives in Rn. And now, of course, well, if we want to consider all n-dimensional vectors, this is nonsense, right? The linear map from Rn to Rm won't be injected. But so, of course, what we want to do is we want to restrict the set of vectors which we consider. We want to put some bound, in some sense, on the complexity of the vectors that we consider. Okay? And there is a rather famous theory which goes back to people like Donohoe, Romberg, and Tao. And what do they have proved? So now I will state in a not really precise manner, but in the spirit they result, which is kind of the heart of this compressed sensing business. So we consider matrix A to be a random Gaussian matrix. Okay, so for random Gaussian A, and now random Gaussian matrix simply means that each entry of the matrix is chosen randomly from the standard one-dimensional normal distribution, and the entries are chosen in an independent fashion. Okay, just that. So this is what I mean by a random Gaussian matrix. No, each entry is chosen in its different. The entries are dependent. No. The entries are an IID standard normal random variables. Okay. So the following happens with high probability. Okay. High probability meaning you pick some epsilon that with probability 1 minus epsilon. Nice thing which I will tell you now happens. Okay. So for high probability of random matrices, the following happens. For each n-dimensional vector n, so I should be very careful because I will be using n and m quite a lot. So I want to make sure that you are able to distinguish n and m. So if n looks like m or if m looks like n, let me know. So the following happens. Now, if this vector has, well, bounded complexity in the following sense. So it is sparse, meaning that there are not too many non-zero entries. Okay, so we only consider those vectors for which the number of coordinates such that xj is non-zero is at most s, and s is a parameter of the method. Okay, so you can think that we consider S sparse vectors, so S is some sort of a measure of a complexity of a vector. Okay, so for all such vectors, the following happens. Indeed, X can be recovered, well, uniquely among those S sparse vectors from Y, so from its compressed measurement, okay, but the heart is not really just that you can in principle recover, but actually they give a explicit and feasible algorithm which performs, okay, so can be recovered via the L1 minimization I will comment on that in a moment, but there has to be, so far we haven't connected N and S and M, and clearly they have to be connected for such a statement to make sense. And okay, I don't want to give you the precise bound, but the bound is more or less that M is supposed to be at least, okay, some universal constant times S. So this is, so M has to be basically linear in S, large enough. And there is also a, let's say, a lower order term, possibly log of N over S. This is N. Okay, now this is not that important for us. What is the precise threshold here? The point is that this is something that is, well, more or less linear in S. Okay, so the higher the complexity of the vector in terms of the vectors that we consider in terms of the sparsity, the higher has to be the dimension into which we compress. Okay, this is somehow the idea. Now, yes.
Well, we have absolute figures there.
There is, so actually, okay. No, it's not. Okay, I can write. So actually, high probability meaning at least 1 minus epsilon. And really what happens here is you also have C2 log something like 1 over S. Okay, this is actually okay, I have hidden this, but this is actually what happens. Now, I don't want to tell you what this L1 minimization algorithm it is. The important thing that it is some sort of convex programming problem which can be solved in an effective manner. If we just wanted to, so this is a side note, but if we just wanted to be able to, in principle, recover an S-sparse vector from its n-dimensional measurement, it suffices to take m equal to S. But then the problem of recovery, which in principle is possible, is NP hard. So algorithmically, theoretically, it's possible, but in practice, algorithmically, it's It's not really something we can. Okay, so this is somehow the first part of the story. From our perspective, this is more about just an introduction what this compressed sensing means. But I should also say that this made into applications, at least into some applications. So there is a
It's not n. So n can be like super long.
in principle, yes. So actually there is this term here. So here is n.
Here is n.
Okay. In principle, here is
N.
n. No. This is n. This is n. So yes, in principle, the larger the n, there is this extra term which requires you to take more and more measures.
I think it's logarithmic.
But it's logarithmic, exactly.
If you think about
This is like, it's very cute, right? Because like normally I was thinking about, using like this, the first criteria, like x(j) not equal to 0, this number to control like some entries here should be all 0, and the rest part can be recovered from the n dimensions. But in this sense, n must be something like m plus s, but clearly this is not.
No. So I guess here somehow the intuition is that you can kind of think that you sit in s-dimensional or maybe 2s-dimensional space by requiring it. Of course, the problem is that if you would fix the coordinates, then you live in an s-dimensional, the non-zero coordinates, then you live in an s-dimensional space, right? But now you live in a kind of union over all the possible directions, blah, blah, blah. So in some sense, at least the way I am thinking about it is that this is somehow, and in some abstract sense, an s-dimensional subset of the n-dimensional space. So what I wanted to say also about this is that apparently this idea has found some applications to things like MRI, magnetic resonance, where because of taking fewer samples than classically, they were able to reduce the time of the procedure. So this is actually quite nice. Yes. So this tau, I think, played a big role in those theorems.
even though I don't remember if it was quoted in
Fields,
because I think it's about the same time.
might be. Okay. The second part of the story, so this was compressed. The second part of the story, which still won't get us directly to our work, but it's kind of is another step of the development that we are after. This is a theory initiated by Wu and Verde. So this is something that might be called, maybe, I think the term they use is almost lossless analog compression. So basically what they said, so this is Wu. So basically what they said is they said the following. Okay, this is all nice, but a very nice, very strong result, but the sparsity condition on the vectors seem very strong. Okay, it poses a very particular geometric structure on the set of vectors that you can consider to compress. So maybe instead of saying that, okay, I want to consider sparse vectors and consider the sparsity as some measure of complexity, maybe we should go the other way around, consider more general collections of vectors which live in n-dimensional space, but in some sense are smaller, and maybe we should consider some complexity measures. Okay, take a collection of vectors, consider some complexity measure, whatever it means, of this collection of vectors, and try to prove that if you control the complexity, then you know something about then you know how well you can compress the sum. This is the first thing. And also they said, why not connect all of this to the classical theory of Shannon of, compression or coding for discrete sources. So stochastic processes taking discrete values in some finite set, and consider an analog of this for stochastic processes instead of a fixed dimension, because maybe then we can use some ergodic theory methods or something like this as well as endoprinting. So what they did, so again, I actually don't want to state any of their results because they are not really important to what I will talk about, but they introduce certain framework, okay? And we kind of, not precisely, but what we do falls almost into this framework, okay?
I think maybe a better than be asymptotic in that sense. No, don't you think?
Might be, yeah. Because if you look at this, it's not clear that it's about stochastic processes, right? Okay, so they want to consider stochastic processes. So, and from now on, basically, from the whole talk, we will consider stochastic processes. Okay, so I will use this I don't know, this double X or whatever, to denote the stochastic process. So this is the sequence of random variables, and we want them to take values in R. Okay, so this is just a sequence of random variables on R, and basically all the time we will be assuming that the process is stationary. So in our words, the distribution on the paths is shifting by. Okay, and they considered the theory of analog conversion. So basically what they wanted to do is they wanted to say the following. Okay, for large n's, we want to find a pair of functions, fn, which goes from Rn and R and n, then Gn, which goes in the other direction. Okay, and these are supposed to serve as, so F is supposed to serve as a, well, as a compressor. So think that Mn is much smaller than n, and you try to compress your n-dimensional data into now m-dimensional data. So you reduce the, and this guy is supposed to serve as the decompressor. So this will be the guy who you are using when you want to recover the original data from the compressed one. And what you want to do here is you want to put some maybe conditions or requirements on those guys F and G. Okay, so often, for instance, we want Fn to be linear and maybe Gn to have some regularity. Okay, which is right. In order to solve this sort of continuity conditions on the inverse, they do introduce some robustness to measurement errors, right? If you know that the compressor is for instance Lipschitz, then you know how the error will propagate back if you perturb the measurement, right? So so with some conditions. So the point is that given a stochastic process, we want to find with as small as possible n's a sequence of functions which satisfy our conditions, which will serve compressors and decompressors, and then there are various how to say performance conditions that you can, or requirements that you can put on this process. For instance, so this almost lossless compression comes from the fact that they usually require that the probability that you make a compression Okay. I will tell you what xn is. So you do a compression and then the compression. And the probability that you will not recover exactly xn is supposed to be zero. Okay. So either at most some fixed epsilon or maybe even just go to zero as supposed to be. Okay, and xn, so this is a notation that will go through the whole talks. So xn, there is no f here. No, we will get there in a minute. So xn or x1n, this is simply the first n. The n-dimensional vector consisting of the first n random variables. Okay, so this is an n-dimensional random vector. And you want to compress it and then decompress it, have some robustness. You know, and with large probability recover exactly what it is. Okay, and somehow the two problems that you can consider here is that somehow the problems. So the first one is the problem of achievability. Okay, so somehow the way that they are trying to construct a theory is the following. So we want to find complexity measures, which, spoiler, can be thought of as some sorts of mean dimensions of a stochastic process. Okay. Find complexity measures, maybe measure. So I will just call it comp for now. There are various choices of the stochastic process. So you give me a stochastic process, I give you a number, and I hope, and somehow the goal is to find this complexity measures in such a way, such that if now I take a sequence, so it's for each n there is some prescribed dimension into which I try to focus. Okay, and I want to do it in such a way that now if I take my sequence mn in such a way that lim of mn over n is greater than this complexity measure. Okay, so I am somehow trying to compress above the complexity measure, right? So somehow I have more space here than this mean dimension. Okay?
This would be S.
Yes, so basically, yes, exactly. So basically of this you can kind of think, in this case you can kind of think that this is, I guess, something like S over N. Okay, then, well, there exists a sequence Fn and Gn, well, satisfying. Okay, and they do have some results of this, which I don't really want to discuss in the details. I will discuss one result in the spirit in a moment. Yes.
Alright.
This is why this is kind of. No, in principle, you know, M is supposed to be yeah, I think up to a constant, this is more or less the idea, right? So one way to define a complexity would be to say, okay, I look at the n-dimensional measure, n-dimensional vector. I look at its maybe sparsity. I look maybe sparsity of the support divided by n, let n go to infinity. This is some crude complexity measure. Okay, and then there is a second. There is the inverse problem or the converse. Ideally, we would like to be in the situation in which this is optimal. Okay, so converse would say that on the other hand, if this lim of mn over n is smaller than common, then well, group FN and GM do not exist. Okay. This is all maybe not very precise, but hopefully you see the spirit, right? You want to say, okay, you give me a stochastic process, I calculate some complexity measure of it, this gives some number, and this number tells you that, okay, if I try to compress above the rate which is given by the complexity measure, then I will be successful. And if I try to compress with rate below the complexity measure, I am successful. Okay, this is all very abstract, imprecise, and so on. So now I would like to talk about further, and this will be the last part of this sort of introduction. One more result by Jalali and Poor, where they, for a certain problem like this, which is, well, okay, you will see, it's maybe in spirit even closer to compressed sensing, they get the achievability result, and with Jonathan, we prove the converse. So we basically prove that whatever they did is optimal.
If I may make
Yes, of course.
For those of you who are familiar with Shannon flows, so when we have a finite alphabet, we try to compress, this is very similar, right? And the point with the Shannon theory is that it shows that entropy is optimal.
Exactly.
And has exactly these two properties. So this is modeled on something very classic.
Yes. Of course, here somehow the switch to this analog. So analog here comes from the fact that the signal can take uncountably many values, right? Not discrete like in Shannon case, but this is just a continuous signal. So of course, well, entropy is infinite and so on. So somehow the geometry of the space and the signal has to come into the play, and this sort of continuity conditions on the compressors and decompressors, they become crucial. Okay. So now we will talk about work of Jalali and Poor. So all those I am talking about complexity measures. In the work of Wu and Berger, also that you will see in the work of Jalali and Poor, geometry or geometric measure theory comes here by supplying some notions of dimensions, which one uses in order to define this complexity. So this somehow becomes more and more geometric. Okay, so the complexity measure which they use is what they call information dimension of a stochastic process, and we will call it mean information dimension of a stochastic, because really in spirit this is some sort of a mean dimension. So in order to define it, so assume that we have this stochastic process. Now, okay, so they only consider, so I will do the same, only they assume that the alphabet is bound. Okay, so let's assume that the alphabet is just a unit interval. And they define, so I will denote it by mean information dimension of the process. This, the upper, we can also define the lower. So this is limit ascending to infinity. Information dimension of a finite dimensional vector, which corresponds to the first n random variables, right, divided by n. So maybe there is a discussion between this because mean information dimension, or maybe a projective mean information dimension, I guess, as the Roman would say, but okay, let us just call it mean information dimension. And I guess I should tell you, so this is, so in other words, I will also use this notation, this is limit ascending to infinity. Information dimension of the n-dimensional distribution of the process. Okay, so mu n, this is n. Okay, so mu n is the distribution of this random vector corresponding to the first guys. And I guess I should define or maybe remind you of the information dimension of a measure in a finite dimensional space. Okay, so this is this and so the upper information dimension. So think that now mu is a measure on Rn. Okay, mu is a measure on Rn. So this is the upper limit. This R goes to 0 of the following. So what you do is you integrate the logarithm of a measure of an R ball round point divided by log R, and to integrate this with respect to x. And I guess to make sense of this, we formally want to integrate over the support of the measure. Okay. There is also another expression which is more directly related with Shannon entropy. Right. So this is the following. This is again in soup. As R goes to 0, and you calculate Shannon entropy of the measure mu with respect to a partition which I denote PR divided by log R. Okay, and this PR, so PR is just partition of Rn into how to say cubes. Cubes with vertices on the lattice R Z to power n. Maybe it's better to just make it right in 2 dimensions. We would just take the grid. Maybe here is 0, and we just take a grid of silent, right? All of those guys are of silent, right? And this is just the usual Shannon entropy of a partition with respect. Okay, perfect. There is one more notion that I need in order to state the results. Then we state the results, then we state our results, and then we talk about the okay. So the Jalali and Poor result, whatever it is stated not for all stationary stochastic processes, but for ones which are in some sense strongly mixing. And this is the notion of the so-called psi-star mix. So we will say, so this is the definition. So we will say that a process X is psi-star mixing. The following holds. So if limit as G goes to infinity of a certain function psi-star of G is 1, and now what is this? So this psi-star is a certain mixing coefficient, right? Which is defined as follows, where this psi-star coefficient of G, so G is a natural number. This is simply the supreme. And what you do is you look at all the ratios like this. So probability of A intersecting would be divided by the product of the probabilities. And of course, the point is that you take those A and B from sigma fields which are well governed by G, right? So this simply means that A is in the, so you go over all J's at least 1, you take A from the sigma field generated by X1 up to Xj, and then you take B from the sigma field generated by everything that starts with J plus J. Okay, so this is, I guess, a rather strong mixing condition. So definitely all IID systems satisfy this. Some, well, Markov processes, at least on finite state space, well, mixing Markov process satisfy some things like moving averages of processes which satisfy this, things like this. Okay, but in particular, IID processes satisfies this, and it seems that the results are already non-trivial for IID processes. At least this was our impression, I think, at least. Already for whatever we talk about is non-trivial already for IID processes. Okay. Okay, and now here comes a theorem for Jalali and Poor, of Jalali and Poor. So this is Jalali and Poor. And they put the following. So first I will just write it and then I will make all the things. Okay? So, given a sequence. So you give me a sequence MN. Okay, this will be the sequence of dimensions into which we try to compute. There exists a sequence of functions Fn, and now this function Fn, this will be essentially those compressors. So they are supposed to go from R and N. But the point is that, so maybe to relate to this theory. I promised to first write everything and only then comment, but I am not very good at keeping promises. So, in their theory, it will be similar to the compressed sensing in the sense that the compressors will be random Gaussian matrices. And we want to say something with high probability about compressing with random Gaussian matrices, but with the dimension going to infinity. Okay, so formally, what this function will do, it will be the decompressor, so it goes from R and N, but it is also allowed to know what was the matrix which we used to decompress. So this is the type of N times N matrices, and it is supposed to go back. Maybe it's unclear what is the meaning of this function. It will become clear in a moment. And now the functions are such that for every stochastic process, well, on 0, 1, okay, which is also C-star-Dixon. So the following holds for all C-star-Dixon stochastic processes. Okay? Note, this is kind of important, that those functions do not depend on the process. This is why I have stated it in this order. Okay, there exist functions such that something happens for all the stochastic processes. If the limit is n goes to infinity of mn over n, so the compression rate that I'm trying to achieve, if this is greater than the mean information dimension, the upper mean information dimension of the system, okay. Yes. Yes. No. So this will be the decompressors.
Okay, so we go back to dimension.
This is n. Because I'm compressing from n to n.
Yes.
So when I go back, I have to go back from n to n. This is my n. This is n. Okay. Maybe if I write down what happens in the theorem to.
You didn't mention anything about the compressor. Maybe this is what is confusing.
Maybe this is what is confusing. So let me finish the statement, and hopefully the confusion won't be as large as this. Okay, so for every stochastic process and a sequence AN, well, okay. So this will be the compressors. They go from, so these are matrices n times n, not n depends on n, sequence an of independent random Gaussian matrices. Okay, so what I do is as compressors, I just choose random Gaussian matrices, just as in the very first theorem. Okay, the following happens. So now I let the dimension grow. So for each n, I have matrices of different size. I assume that everything is independent from everything. Okay, so all the entries are independent from other entries, from other n's, and also independent from the stochastic process. Okay, so you give me such a stochastic process, you give me a sequence of random independent Gaussian matrices, and then the following holds. Okay, so what I do, so xn is my original signal up to time n, right? And then what I do is I compress it by a. an xn, this is something that lives in m-dimensional space. This is the compressed signal, right? And now I decompress it. So what I do is I apply fn to it. So this will give me some now n-dimensional vector, but also the compressor is allowed to know which matrix I have used to compress. Okay, so now this will be again something that lives in Rn. So it makes sense to consider the distance, the Euclidean distance between those two vectors, right? Okay, I normalize it by the square root of n, and this field will go to 0 in probability. Okay.
So the figure is belongs to R and times n.
Yes, yes. So these are n times n matrices. So this is a matrix which, when you apply it to n-dimensional vector, will spit out for you an m dimension. Okay. Maybe I should just make a picture. So here I have x, y, n. This lives in Rn. Right? I apply to it this random Gaussian matrix, so I will an xn, this lives in Rn and n. Right? And now I try to recover. And I ask how good is it recover? Okay, and the theorem tells you that the decompression will be successful asymptotically, but the convergence is improbable. Okay, and I should emphasize that the randomness, the randomness which accounts for this convergence in probability is both in X and in A. Okay, so in some sense, this is a strong requirement in the sense that it requires that the error is small for high probability of AS.
What convergence in probability means?
Yeah, so convergence in probability means, maybe I will just try to think. Okay, so it means that, let me just write it like this. The probability that the distance between xn, so xn is the sequence of random variables, this is the limit, this is the supposed limit. The probability that this is delta goes to 0 for every delta. Okay, this is the for convergence in probability. So it is bigger than almost true convergence. So we don't claim almost true convergence here. I don't know, maybe it's not true. I don't know. But this is what they have. And also, so there is this strange 1 over square root of n here. But this is really so, okay, I need to erase something. So I guess I will erase the consistencies. So I will often denote the recovered vector as x hat n. Okay, x hat n is this thing a n x n a n. Okay, and this 1 over the square root of n, this distance. So the distance between the original vector and the recovered one in the L2 norm, right? This is nothing else. So if you go inside 1 over with 1 over the square root of n inside the norm, and you write down the norm as a sum, you see that this is maybe after squaring, this is an average of just the distances between the j coordinate of this vector minus the j coordinate of this vector, right, square. So saying that this goes to 0 means that this is the average mean square error condition, basically. Okay. Which also shows that this is somehow the square root of n is somehow a natural normalization. Okay, great. Now, why am I talking about all of this? Of course, I'm talking about all of this to tell you what we have proved with Fiona. So what we did is we simply proved that
something is will.
Yes.
The left-hand side there is a square in the end, square root.
Yes. I guess.
You wanted maybe to take square.
Yes, I guess like this.
Ah, okay.
Yeah, I think now it's correct, right? Yeah. So with Jonathan, we have proved that. Okay, sorry. One more about those effects, because they say I noticed like this, there exists a sequence of effects, right? The point is that those effects, they are given explicitly. So I don't want to tell you how they are given, but they simply give an algorithm, which they call minimal entropy pursuit. I think I don't want to tell you how it operates. It has something to do with first, quantization of your continuous data to some grid, and then minimizing some entropy, like some sort of empirical entropy functional on those grids. Okay, I don't want to get into it, but the point is that this is explicit. Okay. What we proved with Jonathan is that this condition is optimal, in the sense that if you try to compress below the mean information dimension, and still with random Gaussian matrices, and still try to keep this condition, you will fail. And moreover, you will fail not only for their specific construction, but for any sequence of Borel compressors. Okay, so, and somehow what made this all difficult is the fact that we couldn't assume any continuity or any regularity of the decompressor maps, because in their case they are not even continuous because of this quantization, which is okay. And this Hubert theorem, it provides some converse theorems, but it always requires some regularity of the decompressors, right? And somehow what was difficult for us was to deal with the non-regular, just measurable, which is not. Okay, but let me say yes.
When they didn't consider the L2.
That's true. This is the stronger requirement, L2. Yeah. Okay, so maybe here I will state our result, and for that I need, so it's, well, there is actually one extra thing we require with respect to those guys. We require some, I think from the point of view of information theory, mild regularity condition, geometrical regularity condition on the finite dimensional distributions. Namely, we want all of them, so this is, I guess, the definition. So I will call measure mu, which is a probability measure, let's say, on Rn, is local dimensional regular, simply if the local dimension exists at almost every, okay, which means that if the local dimension, which I will denote by being x, which is by definition lim as r goes to 0, logarithm of a measure of a ball around x divided by logarithm of the radius, if this exists at mu almost every x. Okay, so all nice measures were all, I don't know, volume measures on, or absolutely continuous measures on manifolds, but also lots of fractal-like measures of similar measures, blah, blah, blah. Many measures satisfy this, especially when they have some dynamical invariance under some nice dynamics, okay? So this is, we also had a result without this assumption, but we'll get there. So our main theorem, so this is the one from the paper with Jonathan, is that, okay, so if X, the stochastic process, is, well, maybe satisfied. So first, okay, we assume that the variance, so variance of the first, have I said, okay, so all the time I consider stationary, okay, all processes are stationary. So we want the process to be of finite variance, which is actually a weaker assumption than leaving on 0, 1. Okay. We want C star with C. And we want all finite dimensional distributions, local dimension regular. And then, well, so these are the assumptions, I think. Then, if linking as n goes to infinity, n over n is smaller than the upper, I mean information dimension. Then for, well, okay, any Borel sequence of those recovery maps at n we have this mean square error xn minus x and hat does not converge to 0 in probability. And what I haven't written down, but the process included here, it's the same setting. So this is for a sequence of random Gaussian matrices. Okay. So you see that this is even in some sense better. This is in some sense a stronger converse, a strong converse to this, in a sense that a feature of this theorem is the inversion. Fn doesn't depend on the process. Okay, so these are just some functions that you have a priori given, and whatever the process is, if it satisfies the condition, the thing will work. Now this, maybe it's not clear from this formulation, but here, even if you would allow Fn to depend on the process, you will still fail in the sense that this will not. So this is even a converse to a non-universal version. Okay, but this is a sign. Now, I have like 30 minutes. So now I want to try to say something about the proofs. Okay? The proofs are quite technical, so I won't show you any details or anything like this, but just the somehow morally what happens, where the inspiration comes from, and so on. And maybe if I will be fast enough, I will try to explain to you what one has to do in order to make the proof, but not how we do it. Okay? So, we had a very precise inspiration from geometric measure theory, and this is where geometric measure theory will come to the play. Namely, the Marstrand slicing theorem in the version for measures. Okay, and Marstrand slicing theorem, as in some sense, gives the answer to this problem, to the converse, in a finite dimension. And the whole deal will be to control and understand what happens when the dimension goes to infinity. So, there is a theorem. So this is Marstrand. Okay, I call it Marstrand's slicing theorem. But really the version I am interested in, this is a version for measures, not for sets. And this is due to Yarvenpa, and now there are accents here, and Matila. This is Marit, I think. But okay, maybe I shouldn't have said that. Yarvenpa, so I think it's not. Okay. What does it tell you, this theory? It tells you what happens when you take a measure of large dimension and you try to project it randomly into a subspace of a smaller dimension. And it tells you, in some sense, that the slices, the conditional measures, are non-trivial. And this is really what we are after. Okay, so mu, I want this to be a Borel probability measure n, such that there is a couple of ways to define it, but I want it to be such that the upper half of the dimension of scalar, which is by definition the essential supreme of the lower local dimensions. So you see, here I defined the local dimension by requiring that the limit exists. But of course, this limit doesn't have to exist. If it doesn't exist, then we have the upper and lower local dimension. This is the lower one. Okay, so the lim inf, and limit always exists. Okay, and this is essential supremum, well, where x is considered as random taken with respect to t. Right? And I assume that this is greater than m. Okay, so see that, okay, this is somehow dimension smaller than n. This is in some sense similar to this condition, but here we have a finite dimension, fixed one. And then for almost every linear subspace V, so this is supposed to be a linear subspace of Rn with dimension n. I will make a picture. We have the following. Here is some notation. So I look at the measure of all the points in the n. Maybe I will make first that. Maybe it's better for me. So think that this is the subspace V, okay? And somewhere here leaves my measure V. Okay? And now here I have the map. Here I have PV. This is the orthogonal projection of PV, right? And then if I have a measure in the map, I can consider the conditional distribution, right? So what happens is I can disintegrate the measure U into a bunch of measures which live on the ranges of single points. Okay. imagine that this is orthogonal. Okay? So maybe here is some y, this y is the form of x, and here I see I have a measurement. And the theorem says that with positive probability, those fibers will be non-trivial and actually gives some lower bound on the dimension of the measures that we see on the fibers, right? So it tells you that with positive measure, the upper Hausdorff dimension of a measure, so I denote by mu v px, so x is somewhere here. I look where it projects. This denotes the conditional slice with respect to the projection onto this point. This measure will have dimension at least, well, the original dimension of the measure is 2 minus m. And under our assumption, this is positive, and this will happen in the positive. Okay, and this may be, I don't know, maybe I should write this. So we have this conditional distribution of mu into a bunch of measures. So we can either write it as v px mu x, right? So I choose x according to mu. I look at the conditional slice together. After reintegration, this will give the original measure. Or if you prefer directly on the projection, this is mu y v, but now with respect to the projected measure. Okay? And I don't try to. M is this dimension onto which we project. M is the dimension of the of this. Yes. Okay. What does it have to do with this sort of conditions? Right? What does it have to do? Well, more.
The theorem corresponds to our intuition. Like if everything is regular, we expect this to be true, right?
Exactly.
In the picture.
Exactly. So well, so this theorem simply tells you that if you start with something of dimension greater than m and then try to compress it onto n-dimensional thing, then, well, you cannot really compress it in a sense that the fibers will be non-trivial with positive probability. And morally, this is what we want to prove here, right? That if you try to compress below now the mean dimension of your process, then somehow you shouldn't succeed. Now, so think now. So first of all, here we talk about random orthogonal projections, but it's really for this sort of theorem, it doesn't really matter if we, instead of considering random orthogonal projections, we consider random Gaussian alternatives. It's really the theorem will be true again, right? If I consider random Gaussian matrices which go from n to m, right? So this is first observation. And now you see, so what I will try to do now is I will try to connect this sort of expression somehow with this theorem. Okay? And this somehow will tell what happens in a fixed dimension n. So look at the expression of this sort. So maybe I have maybe let's do it like this. So fix n. So I am in a finite dimension n, right? And I will look maybe now at the expectation xn minus fn, an, xn, an. Okay, and maybe I want second law and I want it squared. Okay. So what is this? This is really an integral. Well, in terms of the finite dimensional distribution and dimensional distribution, this is x minus fn a square, where I take mu x with respect to mu and a, okay, with respect to measuring method g, but g does the distribution of, the distribution of the random Gaussian characteristics. Okay. Now, if I write it, I can write it in terms of the conditional distribution. Because note that this function, okay, it depends on A and it depends on X, but only through where we land in the projection. Think that A is projection doesn't. Okay, so this is really, now I think I have to like a tree to the ground. So I will write X minus F and now also Y. A. But now, so Y corresponds to the Y on this picture here. So this is the projected value. So Y I have to choose with respect to the projected measure here. And now X is something that lives on this file. Right? So here I integrate with respect to the conditional measure. So this is value, I guess I should write A instead of Y X. And then with respect to the integration. Now, why am I doing all this? Take a look at an integral like this. After this conditional disintegration, this thing here for fixed y is fixed. So this is really an expression of the form expected distance of random variable x from some constant. This, but we know what is the optimal vector, or the one that will minimize such square error, mean square error. This is the expectation of this distribution. And then this distance becomes the variance. So really this is always at least a double integral of the variance of this measure of a y d a b y d g n. But now you see, the only way for a measure on Rn to have a finite variance is to be a Dirac mass, right? This theorem tells you that with positive probability, those measures that we look at here, so the measures on the slices, are non-trivial. So with positive probability, they cannot be Dirac masses, so with positive probability, this variance will be positive. Okay, so definitely, and this happens with positive probability of y's, almost purely with respect to A. This is definitely something positive. And now, so if we use this sort of thing to measure the distance, to measure the error, then we see that basically this Hausdorff dimension in a fixed dimension gives the threshold. There is also a compression theorem corresponding to the. So really in a fixed dimension, somehow the Hausdorff dimension via this theorem is the optimal. But of course, for us this is not enough, because you see it might happen that as n goes to infinity, the integrals of this form, they can converge to zero, or maybe converge to zero fast enough so that this goes to zero. Okay, so this means that what we need to do in some sense, or this is what we attempted and succeeded to do, is to try to do this sort of argument using whatever the arguments are used inside the proof of this thing, but with a control of what happens when n goes to infinity. And this turns out to be possible, but quite technical. I won't tell you how the proof goes, but I will tell you what is somehow an intermediate result to this theorem to which it leads. Okay, and what I want to, maybe now I want to. So, if you know a little bit of geometric measure theory, then you probably know that this sort of projection theorems are often usually proved via the so-called energy or the potential. Okay, and because what we need to obtain is somehow a high-dimensional version of this, we also end up working with the energies, but somehow for stochastic processes instead of a single measure. This is another definition. So if you give me measure, maybe a finite measure of n, and quantity S, the S energy of a measure is the following. This is the double integral, the distance between x and y to power minus s, then in x then in. Okay, this is the energy. Now, so what I will do now is I will talk a little bit about the proof of this theorem, but really with a goal in mind to formulate a stochastic processes version of it in some sense. So, in terms of the energy, you can define what's called the correlation. So this is yet another notion of a dimension of a measure. This is supreme over S, such that the S energy of mu is fine. Okay, and this is known to be at most the lower half of the dimension of mu, which is an S in over there, and also the upper half of the dimension. No. This inequality holds always. Inequality. Equality holds in very special state. Okay, so actually, the way to prove this sort of theorems is to first prove it for the correlation dimension, and then do some trick in order to enhance it from the correlation dimension to the half. Okay, and how many details do you want to put? So. Okay, I will lie a little bit. But somehow the limits of the truth of this theorem. So the main step of Marsland is to prove the following inequality, which is not trivially I will tell, but I will for our needs to be closer. Okay, so what you do is you integrate S energy of the conditional measures, right? Well, with respect to the so for each V, you just integrate along the slide on the energies of slices, right? And then you integrate over all the possibilities. Right? And what you do is you prove that this is a constant constant which depends on n and m times the energy. Maybe I want to write like this: S minus n energy, and this is the most S energy of the original measure. Okay, and this uses the so-called transversality technique. I don't want to get into that, but this is somehow morally what happens. Okay, now I want to put this in the parentheses because this is not true as written down. There, you have to do some extra normalization here, which caused us a lot of problems, but I hid it under there. Okay. Okay, so you see, in some sense, morally, what we have to do is we have to deal with the problem which I have just put under the rack. But really, what we want to do, and you see how it goes. If now you take S very, very close from below to the dimension of mu, you will see that if this double integral is finite, this means that for almost every V and almost every Y, this energy is finite, which means that almost every slice will have dimension at least S minus n. And now I go with as close to the correlation dimension as possible, and I get a version of this theorem for the correlation dimension instead of x. Right? And what you have to do when n and m go to infinity, you have to understand, you basically have to understand how those constants behave as n and m go to infinity, if instead of v, you have to you consider the Gaussian matrices. Also, there is this extra problem which comes from the fact that really you have to put here an extra normalization by the density of the projection of mu onto tau, and you need to give some nice uniform bounds on those densities, but this is another technical step. And okay, thinking about this, doing all this, being very patient with trying to control those constants and so on, let us do the following result, which is somewhere here. Aha. So what we did is we have defined what we call, or what we might call, mean correlation dimension of a process, which has something to do with this definition, but it's not. So the mean correlation dimension, or the correlation dimension rate, now of a stochastic process, is the following. So this is again supremum. Now I write theta, so maybe I will say supremum over thetas, such that the following holds. Mean sup as n goes to infinity of 1 over n log theta and energy. Now this would be too simple if I would just write n to power theta n over 2, theta and energy of the n-dimensional distribution of the process. This is supposed to be. Okay, so this
logarithm and brackets.
yes, yes, yes. So this quantity, whatever this quantity is, and I will tell you the moment to this cannot explode faster than this has to be at most exponential. This is what this condition says, right? But this, yeah, very good. So this is really, it looks terrible, but this is really the energy, theta and energy of the same measure n, but with respect to a modified norm on Rn, and the norm, so well, I will call it norm to n, and norm to n is just 1 over the square root n of the usual norm. Okay, so this is basically the normalization which makes so the unit cube in Rn has L2 diameter of the order square root of n. And this normalization makes a unit cube to have a unit diameter. Okay, and then with this, maybe I will just write it here. So main theorem holds, well, let me just write it like this, holds for general processes, well, maybe under the condition that linking of n over n is smaller than this mean correlation. When I say general processes, I really mean that we do not assume, well, we don't have to assume this. Okay, and what's most important, we don't have to assume the precise termics, okay, which is somehow from the point of view of the theory of stochastic processes, this is a rather strong requirement. Okay, so we actually have well, lower bound for the compression rate for very general sources. But unfortunately, we know that this is not optimal. This is not optimal. Okay, and this is first problem. The second problem is that it seems quite challenging to calculate this mean correlation dimension directly for specific examples. So basically, we don't have other example than IID, uniform distribution on an interval, for which we can actually calculate. But the point is that just as for this theorem, this result for correlation dimension can be used as a stepstone on which you make a step and then you jump to the Hausdorff dimension. We can do something similar with the mean correlation dimension and mean information dimension. But this is again another quite technical part of the story. So I still have 5 minutes. So maybe I will try to say at least something about how we go from this main theorem. So maybe this is, I don't know, this is main theorem 2.
Actually, you have more.
I have more. Okay.
Get you wish.
Okay. Maybe I will. Okay, I hope to say something about what actually happens in the proof of going from this to there. I probably won't manage, but I will try to say this some. So, where does the psi-star mixing condition actually comes to? Right? The psi-star mixing condition comes when you try to go from this theorem 2 to theorem 1. And it is used via the following proposition, which we can prove. So there is the proposition. So if you have X, which is well, stationary. Okay, I don't write stationary, everything is. So it's a psi-star mixing with finite variance. Okay, this won't be again a correct statement of the proposition. This will be a simplified statement, but for the discussion, actually, will be well, more useful in the sense that I'm not going into the details, which are somehow technical, but blah 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 blah. So then, for every theta, let's say, there exists a set En in Rn such that the process, so the n-dimensional distribution is has one minus eta measure concentrated on En. So these are large sets, these are almost full sets. So limiting this goes to infinity of mu and of En is at least one minus eta. Okay, these are large sets, but what is crucial is that the mean correlation dimension, and now I will write something like this, of mu n, of the sequence mu n restricted to En. Now previously I have defined the mean correlation dimension for stochastic processes, but actually you see, this definition makes sense for any sequence of measures, if the nth measure is on Rn. So actually I can consider it for such a sequence of restrictions. So this is the measure. A measure like this is a measure on Rn. And now I have a sequence of them, and I can talk about this condition from the mean correlation dimension. This is at least something that we call one more notion of mean dimension. Lower mean average local dimension of X minus eta. Okay, so this correlation dimension, I can make it as close as I want to this quantity. I will tell you in a moment what it is. which means that using this theorem, I can actually get a version of this theorem, but with this mean average local dimension replacing mean information there. Okay, so actually, if I would get rid of this condition of local dimensional regularity, which is not used over there, I get a version of this theorem, main theorem for mean average local dimension. What it is? Well, it's just the following, where this mean average local dimension of the process is just, so it's in as n goes to infinity. And now what I do is I look at the n-dimensional distribution and I just integrate the lower local dimension. Okay, so this is like an average local dimension of a measure, right? I just look at the local dimensions, integrate. I take the average, and of course, n goes to infinity, so I want to have 1 over n. Okay. And there is another lemma. That if mu n are local dimension regular, then this thing coincides with the information for reasons which I will not which I don't notice. Okay, and this is how you finally arrive at this theorem. And of course, the interesting thing is how to get this proposition. This is something standard in geometric theory. This proposition is something interesting, and I guess okay, so I will tell you what I will not tell you about. So I have prepared a sketch of the proof of this proposition for the case of IID systems. And this was already difficult in the IID case. And somehow the whole problem, I will just tell you what the problem is. The problem is that, okay, we want to bound energies like this. There is an alternative expression for an energy, which is S integral from 0 to infinity, r to the power minus s minus 1, measure of an r ball, and I integrate this with respect to r and then with respect to s. Okay, this shows you that in order to bound, we want to bound mean correlation dimension from below, so we need to, well, find thickness for which this condition holds. So we need to bound energies from above, right? Bound with energies from above, we see from this condition, from this expression, that we basically need to have a good bound. You need to have a good bound for a measurable bond, maybe r to some power s, which holds basically on a nice set, on a large set like this, which holds uniformly with respect to x and r. Okay, this is somehow difficult. And if you are an IID measure, this will be, I guess, 2 last sentences. We insist on working with the L2 norm. We insist on working with the L2 norm because, well, we want to match the Jalali and Poor result who worked in the L2 norm. And also there is this nice interpretation as a square, mean square error, blah, blah. So we want to work with the L2. So this means that in our case, we have to look at n-dimensional distributions and look at the L2 measure scheme. And now, even if your measure is Bernoulli, so it's an IID, we are in the IID case. If we would be allowed to look at the L infinity balls here, life would be much easier. Because if you get, if we are in the IID case, so maybe, you know, mu n is some marginal measure n-fold composite n-fold product, then a measure of an infinity ball of XR will be simply a product of measures of one dimensional, right? XR, right? And using this is the sort of quantity that we can control using some sort of ergodic theory methods, because you see that if you take a logarithm, this is like a Birkhoff sum of some potential. This is something that you can play with, and actually you can do it, and somehow controlling this is nice. But the problem is that we want to work with a n-ball, with a L2 ball. And of course, you can always bound the n-dimensional L2 ball, always sits inside L infinity ball. And if you are in a fixed dimension, the two norms are comparable, they are equivalent, and it really doesn't matter which norm you work. But because we need to have a tight control of what happens as n goes to infinity, it turns out that a bound like this is too crude. It's like we are actually off precisely by this ugly factor here. Oh, okay, not exactly, but of a factor of this order. So this destroys this is too crude, and somehow the difficult thing is how to arrive at a much better bound, which actually uses the fact that L2 ball is much smaller than an infinity ball for large dimensions, and this is the technical work that we do. I don't know, maybe technical. This is the work which we do in the paper. Thank you very much.
Any question?
So just to check that correctly from the beginning of your talk, so there was a result about the sparse situation. So there you had sparse.
Okay, yeah.
Then you had m rather like logarithm of n, right?
There was the logarithmic factor.
Dependent also.
Yes.
On n independent like logarithm.
Right. But the point is that on S, so the sparse, which is somehow the analog of the complexity measure here, the dependence was linear. Okay, but sorry, maybe the question is different.
No, more about this. That here m depends linearly on n.
Yes.
Logarithmic.
No, there is
log n.
yeah.
So kind of the sparse situation is much kind of better than you can take much better result. Is correct?
Well, yes. So the point is that sparsity, in the sparse case, you get much stronger results, but this is because you assume a very sorry.
Very interesting. You can also consider the asymptotics.
That's true.
And then you recover, right? This is what we saw by the work of Candles.
Yes.
It's very interesting. There is a paper by Candles, right?
I think so.
Where he and co-author, they consider the asymptotic sparse regime. And then you see actually that, but it's very exact on it.
Yes. So somehow the point is that sparsity is a very strict geometric condition, right? And here, you in some sense allow any distributions as long as they are not too complex, where the complexity is measured by this information I mentioned. Maybe I can say that it's open. Like in general, can you get a nice type result where you remove the system mixing condition? We only have this mean correlation one, but this one is definitely not optimal and not very user friendly because we don't really know how to calculate this stuff.
Probably there is also a direction which is, this is asymptotic complex thing. You should also be able to remove the time stabilization.
The
Time stabilization.
to consider continuous signals also in the time domain.
That's probably even the next.
Right.
All right, let's thank Adam again.
Thank you.